Okay, let's start. So if you haven't finished the quiz, and then yeah, please do so as soon as possible. Okay, so yeah, we are studying chapter 6 about training our neural nets, and then we discussed about the disadvantage of having all the positive or all the activation values that has the same sign. So if we use the sigmoid as the nonlinear output unit as the, from the previous layer, and then it will generate all the output values that are positive numbers. And then once they are used as an input to the next layer, and then it will just end up giving all the positive signs of the gradient to the associated parameters, right? So we saw this kind of example, although it's a little bit messy, but yeah, if we have three different input nodes in our input layer, and then we can think of this associated parameter values, and then given the same gradient value that are coming from the later layers. So it is called the upstream gradient, right? In the CS231 lecture. So this is a upstream that are coming from all the final node to the input layer or input node. Okay, so given the same gradient value, and then if all the x1, x2, and x3 are having the same signs, and then they will give the gradient with respect to a, b, and c all has the same signs of the values, right? So that way, within one iteration, a, b, and c will have all the positive gradient or all the negative gradient. Okay, so that way, if our optimal value of this a and b has different signs as our optimal values, right? And then if we start it from here, and then the gradient descent update will become quite inefficient, because we have no way to directly go to this direction that has different signs in terms of the gradient of the a and b, right? So in this particular case, the gradient of an a will be positive, and b will have the negative gradient, right? So in general, having both signs possibly as our input node to a particular layer will be preferred or desirable, rather than having the same signs of an input elements in our layer. Okay, so yeah, in the case of ReLU, that also has the same problem or issue with the sigmoid that has the same signs of the gradient, right? But in this case, I think I described it in like earlier lectures, maybe 2 or 3 weeks ago. In the case of ReLU, it can be viewed as updating our parameters only partially, right? So if the forward pass had a negative value, and then passing through the ReLU, and then it will produce 0. But then when doing the backpropagation at this ReLU node, and then if the forward pass had a 0, negative input, and then the gradient will become 0. And so, yeah, so if the ReLU output was 0 because of the negative input, and then the backward pass will have completely 0 gradient, and thus we will have the effect of updating some subset of the parameters, right? Yeah, only for those that have a positive activation value given to the ReLU layer. Okay, but still, for those nodes that has a positive activations as an input to the ReLU node, and then they will all have the same kind of signs as well. So ReLU output will be either 0 or positive values. So having the same signs for that particular subset of the parameters to update. So this kind of limitation or problem of having the same sign will still hold true. I mean, they will still exist in the case of ReLU as our nonlinear unit. Okay, then let's see. So there was a question about this dead ReLU. So dead ReLU is let me explain this in a little bit more detail. So consider multiple output nodes, and then we have maybe 2 input nodes. And then this output node, I mean each output node will have its own linear transformation equation, right? So suppose this first output is maybe 3x1 plus 2x2, and y2 is negative x1 plus 4x2, y3 is 2x1 minus x2. Although we can have some bias terms like 1, negative 2, and 4. These are just a random number, and suppose this is the current state or current parameter values during our gradient descent update. Okay, and then let's consider this is our first layer. Okay, and then this one is maybe height or weight. Okay, and then and then our suppose our training data is composed of 100 points, right? And then we will have 100 vectors that are composed of this height and weight pairs, right? And then we can think of this activation value through this linear combination for each of 100 different training data, right? And then we will have some set of 100 numbers and another set of 100 numbers, right? And then in this case, the dead ReLU refers to the node that has all the output as negative values. Okay, so suppose the first training data item is 2, 1, and then what about this activation map? Activation value, it is 6 plus 2 plus 1, so it will be 7. And then let's think of the second data item that has the input feature vector as 1 and negative 3, for example. Okay, so in this case we will have some activation value, right? And then let's think of this node. In this case, given the first data item 2 and 1, okay, so let's change it as 3, and then it is negative 1, right? Okay, and then for the second data item, it will have its own activation, right? So for negative 1, and if we plug 1 and 3, then 12, and it will be 9, right? So let's think of this weight associated with this second node, okay? And then let's consider when those two weights are updated. When having this negative output as this linear combination, and then once we use the ReLU right after this linear layer, and then it will be, this negative 1 will become 0, right? And thus, so bringing this node as, and then we have a ReLU over here. And then, so here the forward pass has the output value as negative 1, and then the output of ReLU will have 0, right? And then what about the backpropagation in this case? Suppose dy at this point is -2, for example, and then if the ReLU activation was 0 because of the negative input, and then this one, the corresponding gradient will be 0, right? Does it make sense? Yeah, because our ReLU function is something like this, and the current activation was the case where we have an input of -1 and then output is 0, and then when doing the backpropagation, given this gradient, we will just multiply the slope at that corresponding point, right? And so at this point, the slope is 0, right? So that slope is multiplied with the dA, and that will produce the gradient corresponding to this input node to the ReLU, right? And so once we have this negative region as our input to the ReLU, and then regardless of the gradient value at the output node of the ReLU, it will become always 0, right? Okay, so back to this node. So we arrive, the arriving gradient is 0 actually, right? And then the weight corresponding to these two edges will also have 0 gradient, right, all the time, right? So that way these two green weights or these green edges will not get updated, right? And then when do they get updated? Yeah, it is when we have positive activation value given to the input, given to the ReLU unit, right? So in that case, that's when we can update those two edge weights, right? So among our training data, and then those two edge weights connected to this particular node, okay? So those two edges will get updated only when the output of this linear combination is positive for subset of our training data, right? But what if all our training data produces a negative value as an output to this node, and then it will become 0 after passing the ReLU. And then what does that mean? Those two edge weights will have no chance to get updated, right? So this is called the dead ReLU, because ReLU output is always turned off for all each of our training data, right? So that is called the ReLU. And what does that mean in practice? During our training, suppose we did a random initialization of -1 and 4, and then all the linear combination output of our training data is producing always the negative value, right? And then starting from this initialization of -1 and 4, they will have no chance to get updated. So they will just stay as just the initially set weight, right? And also, that's not just happening only at the initial stage. So according to our CS231 and lecture, so it can happen during our iteration, right? So they can be updated, but at some point of a particular parameter values, and then suppose, it happened that all the linear combination output corresponding to that node is always 0 for every training data item that we have, and then that's when the updating of these two ways stops, right? So that's that actually makes our ReLU become dead. Okay, so this kind of dead ReLU can be generated during our training, also at the initial stage of our iteration. Okay, then yeah, once we found the dead value at the end of our training, and then that final network is actually equivalent to the smaller network after removing that node. Okay, removing that node. So suppose we have two input node in the input layer, and then the hidden layer has the three hidden nodes, and then maybe two and the one output node at the end, and then this is an FC or fully connected layer plus ReLU, and also this one is a FC plus ReLU. Okay, so suppose we stacked these three layers. Okay, and then after training, after the training is done or the gradient descent update was converged, we found that this node is actually dead ReLU, and this node is actually another dead ReLU, right? And then it means during our training, the output of this linear combination corresponding to each of these two nodes will always produce 0, right? And then suppose this weight was -4 and 1, for example, okay? But for every training example, it will produce 0, right? And then suppose this link has the edge weight as -2, right? And also this link has the edge weight of maybe 3, okay? So in this case, at least for our training data, even though this node will play a role of giving some value to the the output node in the next layer, but the input value corresponding to that node will always be 0, right? So it doesn't matter whatever value we have assigned to these weights, right? Because it will be just multiplied with the 0 anyways, right? So for this for this original network, it will produce the exact same output by just removing this node. Okay, so what does that mean? We just remove this connection, okay, and also we remove this connection, and also what should we do? We also remove these two connections or edges, right? So in that case, we have two nodes and also two nodes in the intermediate layer, and then the next layer, right? So that's the effect. The practical effect. The real effect of removing one node in our network, right? So that is also used in our dropout, right? So dropout has also the same effect, right? So what does it mean by setting the forward propagation value or output value corresponding to that node as 0, and that means we just cut or remove those edges connected from the input layer to that node, and also another edges connected from that node to the next layer. Okay. So in that case, if this guy was also dead ReLU, and then we will just remove these connections, and also remove this connection, right? So these two are exactly the same network. So there is no point of storing those values, okay? Because this network is also exactly the same as the smaller network that has those corresponding edges at all, right? So this kind of technique is also used for there is something called the neural net compression. It is not that important. So so in this case, if we consider this dead ReLU or this kind of dead ReLU node in our network as it is, and then still we have to maintain the weight of this layer as 3×2 matrix, right? But what if we actually remove the dead ReLU and then make our network smaller? And then in this case, we can only store 2 by 2 linear transformation weight matrix, right? So in this case, yeah, we actually need a smaller size of a memory, right? And also during the forward propagation, even though it has some weight values as -4 and 1, right? So in that case, we have to actually compute, or we have to actually multiply with these two input nodes with the corresponding weight values to produce this dead ReLU output, right? But that will be eventually become dead. I mean, resulting in the 0 activation after passing the ReLU, right? So in that case, we might as well just ignore or exclude this kind of computation of this unnecessary kind of computation of multiplying the input nodes with the -4 and 1, right? So that way, not only saving the memory, we can also, compute the we can also save the computing time. Okay, so computation becomes faster, right? Yeah, so that way we can kind of do the post processing of removing these dead ReLU, and also in practice, so once you do the recent homework that came out earlier today, I think, so it is like playing with some neural network structure to increase or maximize the performance of a given task. So in this case, you will typically use a larger network size that is actually necessary for the problem, right? So suppose this kind of problem exactly has 3 layers, and each layer has maybe 4 nodes at each layer, and then we don't actually know this optimal setting in advance, right? And so we typically provide or use our network as a kind of a bigger size of the network that can sufficiently solve our problem, right? So in the CS231 and lecture, the instructor also mentioned that in practice, once you converge or once you finish training your neural networks, then around 20 to or 10 to 20% of the nodes are actually turning out to be dead ReLU, right? So in that case, you can just remove them by just post-processing your network, right? But that's only done mostly when we really have to save the memory and reduce the computation time. For example, suppose you trained your face recognition or face detection neural network, and then you want to load that neural network into your phone, right? And then in your phone, such a computation of this forward propagation will drain your battery, right? And also it will actually introduce some latency for real-time application, right? So during the taking of photos, and then it will actually taking the video streams as an input, right? So it has to guarantee some real-time kind of a response with the minimal latency. So in that case, this kind of network compression kind of thing is quite important, right? And also, we can have this kind of dead ReLU, but we can actually be more active when doing the network compression. So suppose, let's consider some statistics, and then those two are dead ReLU, but for this node, only among the given our entire training data, only maybe 3 to 5% of our data gets activated, producing positive linear combination output. So in that case, it means that node is actually used only for the 3 to 5% of the time given the given kind of training data, right? So in that case, the utility or how frequently or how often this node is actually used in our network, that portion is only like 3 to 5%. So those nodes will be like the ones that we can remove if we want to like more actively reduce the network size or compress the network. Okay. questions about it? And also, this kind of dead ReLU can happen more often when using a large learning rate. Okay, and why is it so? So in the lecture, I mean CS231N lecture, so they mentioned about this mentioning of jumping around of this neural net line. So like this. So why is it kind of dead ReLU? So this thing of consider this as like y. Yeah, so in this case, y is negative x1 plus 4x2 minus 2. So that will be our linear combination 1. And then what will be the regions that will produce the negative output of this linear combination output? And then, so in this case, minus x plus 4y minus 2 equals 0. And so y equals 1/4 times x plus 1/2, right? So we can easily derive this equation for the line, right? So if our two-dimensional input is satisfying, or if that input is on that line, and then that's when our activation or the linear combination output gets exactly 0, right? So that line is something like this, right? So this is exactly when the linear combination output is 0, right? And then when this thing gets negative value, right? So in this case, it will be corresponding to the region where y is lower than this line. So this part is the region where we get negative linear combination output, and this region will produce the positive linear combination output, right? But our training data, such as 2,1 or 3,1 or 1,2 and so on, suppose we are given 100 data items as our training data, and then those training data items are actually fixed in advance, and then we can represent them as like those kind of points, right? And then we can roughly think of the main regions where the data are placed or located for our training data, right? And then this kind of the equation for our line is actually changing per each iteration of the gradient descent update, right? So sometimes if it happens that our line is formed in this manner, and then this region is becoming the positive output value, and then this one is negative output value, and then that's when this ReLU unit gets dead, right? So once we update once we do the gradient descent update, and then this line gets changed into a different slope and a different y-intercept. So in that case, our data are all fixed. So once this kind of phenomena happens, and then this becomes the dead ReLU, and there is no opportunities or no chances to get updated for the corresponding parameters, right? Any questions about it? Okay, now let's think of this leaky ReLU. So the main advantage or the main property of this leaky ReLU is actually not entirely killing the gradient on this negative region, right? So initially, in the case of ReLU, it was completely flat. That gives us the zero gradient, which entirely kills the gradient, right? But if we have this kind of slope, and then the gradient can survive, right? But that gradient will really become small, right? So if our, so this is a leaky ReLU, and then the forward propagation was 5, and then the output will be negative 0.05, right? So this is the forward propagation output, and then suppose the gradient arriving at this node was maybe 3, and then what is the gradient corresponding to this input node? 3 times 0.01, right? Because over here negative 5, and then what is the gradient corresponding to that point? So we have to multiply that slope, right? And so it will be 0.03, which became really small, but it is not exactly 0. So we still update the corresponding linear combination weight that produces this output, right? So this is the main kind of advantage of this leaky ReLU. And how do we obtain or compute this particular value of 0.01 or something? This kind of value is set as a hyperparameter, so we have to set it in advance in the case of leaky ReLU. But at the same time, this value can be also set as a trainable parameters, right? So in this case of this parametric rectifier unit, and in this case, so we fixed it. We fixed the positive regions as just 1 times x, but here alpha can be now set as a trainable parameters, which means that we actually compute the gradient with respect to this alpha, and then iteratively update this parameter to find out the optimal value. So that is this parametric rectifier. But again, in this case of a leaky ReLU, so we have to set this guy as in advance as our hyperparameter, right? And then in the case of exponential linear units, so I think I saw the question about this part about exponential linear units. So why does it have the robustness to noise compared to the leaky ReLU? So in the case of a leaky ReLU, so it is a particular line anyways, right? So even though the activation output, I mean the output of this leaky ReLU and the eReLU may be similar to each other around this region, but what about this region? In this region, eReLU will still stay as a really small value, close to 0. But in the case of a leaky ReLU, even though the slope is really small, such as 0.01x, but still for really large negative value as an input to the leaky ReLU, and then maybe 10 to the power of 6, and then the output will still be negative 10 to the power of 4, right? So that way, this value can be really big, right? And so if this value is actually the one that we have to completely remove, and then this noisy information will be passed to the next layer, right? So that way, this eReLU has some robustness, making those outputs in this negative regions still close to 0. Any questions so far? Okay, then let's discuss briefly about this max-out neuron. So in this case of max-out neuron, so you can understand this in a way that it doesn't actually have any additional nonlinear units. Although it has this max operation, but you can basically think of it in this manner. So we have an two output, and then this guy is maybe 3x1 plus 2x2 plus 5, and then it will also have, the second node will also have its own linear transformation representation, right? And then we typically apply a ReLU or any other nonlinear units. But in this max out units, you can think of this as having no additional layer at the end, but instead, in order to produce this single output node, we actually prepare two different linear layers. So yeah, the one set of linear layer is a 3, 2, 3, 2, 5, and we have actually the second layer having its own parameter set as maybe -1 and 5 and 2. Okay, and then here at this node we will have two different output from two different linear combinations, right? And then we pick up the maximum value between these two. Okay, we pick up the larger value between these two. Okay, so that's how this max out nonlinear unit works. Okay, so in this case, again, yeah, although yeah, so it's more exactly, instead of just having a one node, we have these two nodes that is corresponding to this blue lines, and also the red node, and then we will pass it through the max operator or max unit. Okay, so in order to produce a single node, yeah, so we have to prepare for two sets of linear combination weights, right? So in this case, suppose we have, yeah, we have a two output node in this max out units, and then yeah, if we have a, yeah, this kind of input layer, and then how many parameters do we have to have? In this case, I mean, originally in the case of linear layers, and then it will be 2 by 3, right? Because we have two output nodes and the 3 input nodes, right? But in the case of max out layer or unit, we actually have 2 times more yeah, parameters than the typical or standard fully connected layer. Okay. So does it make sense? Okay, and also let's think of their geometric meaning. Okay. So geometric meaning of this is as follows. So if our max of 3x1 plus 2x2 plus 5 and maybe negative x1 plus 5x2 plus 2, and in this case, what is the resulting graph? So we can represent this as a line. Yeah, so let me just remove one variable at this moment. Okay, let's just simplify that, and then we can represent this line as this guy, and then represent another line as maybe this guy, right? So our output will have this kind of thing, right? So we have two pieces of these linear, I mean, this kind of a line that is connected at a particular point at this, right? So it can be viewed as a kind of general form or generalization of of this this leaky ReLU or this P ReLU. Okay. Okay, so we covered that ReLU and E ReLU, Yeah, so I discussed about the network compression by identifying the dead value and removing those dead values, right? But those network compression that actually removes these dead values, so that is viewed as a network compression because we actually removed the, we reduced the number of nodes, right? But in the case of dropout, even though we use only the subset of the node in our network during our training time, but in the case of testing time, we basically use all the nodes, right? So that way, even after, once we finished our training, and then when doing the inference, applying the test data and then making the prediction, this step is often called the inference. Okay, so training versus inference. Okay, so this kind of inference is basically using all the network or all the nodes that are trained by our network, right? So this is not actually network compression, right? You guys understand? Do you guys understand the difference between these two scenarios? Okay, so this thing is, so this is our input image, right? And then, yeah, we in the first scenario, we basically compute the mean image, which means that, so suppose we have 10 different images, right? And then in the 10 different images, each image will have 3 channels, and then, yeah, for this R and G, B channels, and then for this number, particularly placed in the top left part, and then how many numbers corresponding to this position, because we have 10 different images, we have 10 different numbers corresponding to that, right? And then we can just compute the average of these 10 different numbers, right? And so we take this average for these 10 different numbers at each position and also at each channel, right? So what is that kind of average the output or average the result? And that is just kind of average image that we can have from 10 different images, right? And then our average output will also have like 32 by 32, having 3 channels, right? And then this can be viewed as our average image, and then we just subtract this entire tensor from each of our image. So that is corresponding to the first case of subtracting the mean image. And then the second one of per channel mean is as follows. So within the R channel, we have 32 by 32 numbers, which is in total 1024 different pixels within the red channel, right? And then we have 10 different images, and thus, just taking the average across different locations or different pixel positions. So if we collect the R channel values, and then we have in total this number of R pixel values, okay? And then we just take the average among, given this number, and then what would be the average vector if we compute the average in this manner for each channel, and then we will have a single average number for R channel and single number for G and B, right? And then we subtract this average number for R for every pixel within R channel in our given image, right? So yeah, so we basically subtract the same average value for all the different pixel positions within the particular channel of R, G, and B, right? So that's the difference of this per channel mean from the mean image. Okay, and then now let's discuss about the initialization. So we studied the two different initialization called the Javier initialization and also Hay initialization, right? So both of them shares almost the same idea, and so this guy. So if we have a 2 input node and 3 output node, and then the matrix size W, the matrix size of this W will have 3 by 2, right? So why is it 3 by 2? So this y vector is represented as this vector x times our W matrix, right? So this part is actually randomly initializing this whole matrix of 3 by 2 size, okay? But when using this rand n, and then it is initializing, or it is sampling, or it generates the samples from normal distribution that has a zero mean, and also the unit variance or standard deviation, right? And then this part is the important part. So here the fan-in is actually the number of input nodes, which is 2, okay, which is 2. And then it's actually dividing the initialization samples obtained from this distribution by square root of 2, right? Why do we divide it by this number? Can anyone give some intuitions about the reason? So it is the intent of it is to control the variance to have the same value. Let's think of this situation where we have x1, x2, and x3 as our let's consider these are random variable from this unit standard Gaussian, and then let's think of the summation of these three numbers, okay, and then what will be the mean value of these three numbers? You will have 0, right? Because we just added three numbers that have the 0 mean, okay. And then what about the variance? So if x1 and x2 and x3 are statistically independent, okay, statistically independent, and then the variance of this output variable y, which is the summation of the three, is actually represented as the sum of the variances of these three variables, or three random variables, right? So this holds true when x1, x2, and x3 are statistically independent, okay? So in this case, once we add more and more number of input nodes, and then the variance will actually increase, right? Because that is the summation of all the variances of an input nodes, right? And so in this particular case, the variance of on y will be 3, right? So how can we make this variable y as having the same variance as each of our input variable x? Okay, so we want to have the variance as 1. Okay, so in this case, yeah, we can simply divide it by what? 3 or so this is the the relationship in terms of the variance, right? So you guys know this. Two x is equal to um, yeah, variance of an x times what? It is 4, right? And the standard deviation is actually 2, right? And so, yeah, we have the variance of 3, and so we have to have square root 3, and we have to divide this whole equation by square root of 3, and then that will produce the same variance, okay, as the each of our input variable. Okay. Okay, so now in the case of Javier initialization, we don't just consider this simple sum of these 3 input nodes. We actually consider this linear combination of these 3 input nodes, right? And then if A, B, and C are also random variable that follows this normal standard Gaussian distribution, and then yeah, roughly you can think of this absolute value of y is actually, the average value of this absolute value of an A will be just 1. Okay, it's just a rough estimate, but yeah, in terms of the absolute value, or in terms of the magnitude of the linear combination weight of A, B, and C, so that can be thought of as 1 in case A, B, and C follows this Gaussian distribution having a unit variance or unit standard deviation. Okay, so in this case, yeah, let's just simplify this situation by just setting A, B, and C as just a 1. Okay, so in this case, yeah, so we need this kind of the factor to scale it down to have the unit variance in case we have unit variance for each of our input variable. Okay, so this one is actually playing the role of dividing the square root of the number of an input node, so that the variance of each output node remains the same as the variance of each input node. Okay. So here again, the input if input node has the variance or the standard deviation as 1, and then if we randomly initialize A, B, and C from this distribution that roughly has the value of 1 or -1, for example. Okay, in that case, the simple scenario will be just the same as like this case, and then this random variable, when dividing it by square root of 3, and then now this resulting random variable will have the same variance or standard deviation as the standard deviation or variance of each of our input node. Okay, so that way, even after we pass it through our fully connected layer, the variance of each node in our output layer will stay the same as the variance of each node in the input layer. So it will not explode or shrink down the magnitude of these activation value or the output value of these output nodes, okay, compared to the input node. So does it make sense? 이거 다 이해가죠? Yeah, but yeah, let me add one little thing. So I mentioned about this absolute value. So of course our parameter value can also have a negative value, right? So we can roughly think of these parameter value as plus or minus 1, right? So in this case, yeah, so x1 minus x2 and x3. So what is the variance of y in this case? So in this particular case, the variance of y is still the same as variance of an x1 and variance of x2 and variance of an x3, right? Yep, so that is the main idea of this Hay initialization. So Javier initialization. So if we use that kind of initialization, that scales down this random initialization by square root the square root of the input node, and then that will produce the output having the same variance as the input node. So that way, our distribution of those values, I mean activation value corresponding to those input nodes and output nodes and other nodes in the later layers, that will stay the same roughly, okay, having the same variance, okay. And then what's the difference between this Javier and the Hay initialization? So this Hay initialization has actually this guy. So yeah, instead of dividing it by square root of 3 in case of having 3 input nodes, okay, and then now we divide it by this number, right? So that means we actually multiply it by square root 2, right? Because of this number. I think there is a typo over here. So what's the typo here? So this guy is not 2 over fan in. So it is not. So it is fan in over 2. So yeah, we divide it by the square root of the number of nodes, but we actually increase the variance or increase the magnitude of our parameter by the square root 2, right? So in that case, so x1, x2, and x3 will have the variance of 3 times, the sum of the variance of each of these variables, right? And then now if we consider the square root of this random variable y, okay, so initially y was this guy, and then we consider the square root of y, and then what is the variance of this square root of 2, square root of 2 times y, and that is the variance of y times what? 2, right? So if we use this square root of 2 as an additional multiplier, and then it will actually increase the variance by 2, right? By the factor of 2, right? But why do we use that in the Hay initialization? So once we do this kind of random initialization and then do the linear combinations, and then the distribution will look like this, right? And then it will roughly have the zero mean, right? So half of them will have the negative value and the half of them will have roughly the positive values. But once we pass it through the ReLU units, and then the negative part will become completely zero, right? And so suppose this one is the kind of a distribution of a particular node in an intermediate layer or in a hidden layer, and then once we pass the ReLU layer, and then the half of them will become completely zero, and then what will be our distribution? It will be something like this, right? So yeah, half of them are gone for this negative part, and thus approximately the variance of our random variable became half of the original value once we pass the ReLU unit, right? So this ReLU output will be actually used as an input to the next node, right? And so once considering that output node after this ReLU, and then it has the effect of reducing the variance additionally by half, right? And so our linear combination should prepare for the output that has the twice larger kind of variance of the compared to the input node, right? So if the input node had the variance of 1, and then each of an output layer will have the variance of 2, and then after passing it through the ReLU, and then the variance will now become 1, right? So finally, the variance of this linear layer and then output layer will stay the same as the original input node. So this Hay initialization considers this additional factor of this ReLU. Okay, so Hay initialization will probably be used for when using the ReLU as our activation unit. Okay, and this Hay, this guy has the full name of this Kaiming Hay. Okay, and in the next lecture, I mean, this is lecture 6, and in the lecture 7, when Justin Johnson kind of briefly reviewed the previous lecture material, he mentioned this initialization as a different name. So does anyone remember that name? Does anyone remember the name? It is not that important, but Justin mentioned this initialization as MSRA initialization. So MSRA is a Microsoft Research Asia. Okay, so this Kaiming He once worked in this Microsoft Research Asia, but now he's in Facebook Research, which is a fair. Okay, so Justin called this initialization as a MSRA initialization. So this is just a side story, but okay. And also this Kaiming He is really a big guy, so he invented many of the state-of-the-art neural net architecture, and one of the representative one that he made is residual net. So we will study this in maybe chapter 9 or 10. Okay, and also he also invented a really well-performing network for image segmentation called the mask RCNN. Okay, so just to make you a little bit interested, then so there is a the task called the instance segmentation. So instance segmentation is something like this. So given a particular image, we of course know that there exists a person included in this image, right? And then how many persons are there in this image, and also where exactly are these persons located in this image, right? So there are 4 different persons in this image. So and also the first person is on the left and in the middle and the right, right? So that way we can actually predict or determine the exact location of these images. And yeah, deciding the location of these particular person can also be done really in a detail at a pixel level. So in this case, the first person, so all these pixels are colored by this blue part. So that is corresponding to those pixels corresponding to this first person, and those pixels are corresponding to the second pixels, right? So this is a much more difficult problem compared to just image level classification. So when given a particular image, whether this image is a dog or a cat or a person, okay, so that is just done at an image level. We don't actually need to tell or indicate where exactly that particular object is located in our image, right? So that is like an image level classification, but in this particular task is a much more detailed task, because we have to determine the exact set of corresponding pixels belonging to a particular object, right? So this task is considered as much more difficult task, and this one is called the basically the segmentation task, and for each instance or each object instance, we actually obtain the set of pixels corresponding to that object. So this is called the instance segmentation. So this task is also done by an advanced architecture of convolutional neural nets. Okay, so one of the state-of-the-art method doing this instance segmentation is called the mask RCNN. So that was also invented by Kai-Ming He. So let's discuss briefly about this batch normalization. So batch normalization at a high level, it is composed of 2 steps, right? So the first step is normalizing our data, right? And then the second step, the second step is scaling and shifting these are normalized variable, right? And then see. Okay, so back to this example where we discussed about the dead ReLU, and then it is a little bit messy, but suppose we have multiple training data items where the first one is 3,1 and the 1,2, and then maybe the third one is maybe 2,1. Okay, so we have 3 different data items, right? And then in terms of a batch normalization, this is how we compute this batch normalization. So batch normalization is done at every pixel, at each pixel differently, right? So let's look at this pixel, not a pixel, but at each different node. Okay, so in the next layer we have 3 different nodes, for example, and then you apply the batch normalization at each different output node. But let's pick up this node, for example, and then this output node has the forward propagation output as -1 and 9, and maybe for this input of 2,1, and then suppose the batch normalization, this node has the output of 5. Okay, so we have these 3 numbers, right? And then what is the problem of using these 3 numbers when given to the next layer input? Or what is the next layer? Next layer is our ReLU or any other activation, nonlinear activations, right? So in the case of ReLU, if all the values are negative values, and then it becomes just a dead ReLU, which is not a good thing. And if it is all the positive values, and then is it a good thing? I mean, if our if our linear combination output produces always the positive values, and then there is no effect of adding the ReLU as the next layer, right? So in that case, yeah, it is just equivalent to the case where we don't actually use the ReLU at all, right? And then let's imagine we stack another layer, and then another layer will have linear layer as well, and then we have linear layer and the ReLU and another linear layer. But ReLU actually has no effect because all the values were positive values, right? So in that case, it's just equivalent to just stacking two linear layers. Yeah, basically for our data sets, training data sets, right? So in that case, we don't actually add any nonlinearity to our model. So it's just equivalent to just a single linear layer, right? So it is not a good thing as well for the ReLU. Yeah, so having the positive values as an input to the ReLU is also not a good thing, right? So it will be desirable that ReLU ReLU plays its own role of sometimes creating or making negative values into zero, right? So that's when this nonlinearity plays its own role, right? So this kind of ideal region or ideal input, ideal ranges of an input values to our nonlinear unit is actually the most important part. Okay, so in the case of ReLU, so we want to have our input to the ReLU, in terms of their distribution or range, to be centered at zero. So some of them become zero, where this ReLU has actually its own role, and then some of them will have a positive value. So this is the ideal case, right? But sometimes, in this case, one of them will become zero, and two of them will be just activated after doing this ReLU operation, right? So this is kind of one good case. But what if we just generated our output as all positive values or as all negative values? So those are the cases that we want to avoid, right? So that's why we add this kind of normalization step as an additional layer placed in the middle between the linear combination output and the ReLU input, right? So now when using the batch normalization, we have a linear combination output or fully connected layer, and then we add batch normalization layer, and then we add this nonlinear layers such as ReLU or sigmoid and so on, right? So this is the position where we add this batch normalization, and then the batch normalization is working as follows. So given these number of data items that were collected from our training data, but if our training data is composed of maybe 100 data items and our mini batch size is 20, so at each batch, so we only handle 20 different images, and then we will have 20 different numbers, and then we compute their mean and the variance, so that the mean and the variance of these 20 numbers, 20 numbers become zero mean and the unit variance, right? So in that case, at least those kind of scaled or normalized data will have the ideal range centered around zero and not really wide or not really narrow. Okay, so this is a main intent of the batch normalization. But we actually do the second step of this batch normalization, right? So that is allowing our network to, so at this point, at least for our batch and for a particular node, it has zero mean and unit variance, okay, which is kind of an ideal range as an input to the nonlinear unit, but we actually allow this kind of normalized input to have different mean and the variance. So what will be the mean and the variance after doing this? So the mean will be beta and the variance will be gamma squared, right? Because we scaled gamma and then shifted by beta, right? So beta and gamma and beta are our training parameters, trainable parameters, okay? So they will be updated based on the gradient descent, okay? So we will find those values as an optimal values through our gradient descent. And then what is the effect of that? So for example, in the case of ReLU, I mentioned that we initially set our range of these input to the ReLU as having around this range, right? But suppose beta is 3 and gamma is 2. And then what is the corresponding range? Corresponding range will be something like this. So it got wider and then it shifted to the positive region, right? So why is it beneficial? So what's the advantage of adding this second step? Can anyone answer? So I mean, even though even if our ReLU or nonlinear units has its own role in an ideal kind of situations, right? So ideally, half of them will become 0, half of them will just pass through as a same value, okay? So that will be kind of ideal case. But what is the meaning of that node, or what is the meaning of the activation value of the corresponding node? So in the case of a convolutional neural net or fully connected layers, a particular node can be viewed as a feature extractor, right? So one particular node in the context of convolutional neural net, and that node will work as the detector of a particular edge, or maybe some human nodes, or maybe the tail of cat, for example, right? So each node has its own kind of meaning or a particular pattern that it wants to detect, right? But in practice, if our data set or our 100 items in our training data has actually only three pictures that contains the cat and thus cat's node, for example, right? In that case, that particular node should be only activated for these 3 data items, right? So in that case, 97 data items, their activation should be 0, right? Because our statistics from our training data, or in our data in general, that has a particular ratio of getting activated or having a particular pattern, right? But in the case of human nodes, for example, I mean, suppose in our entire real world, we have 100 different people, but only like 20 cats, right? And then, cats' nodes will be found much less frequently than the human's nodes, right? So in that case, if a particular node is a human node and another node is a cat's node, and then that should be activated much less frequently than the human nodes, right? So this kind of different distribution should be reflected for our neural net, for our optimal performance of our neural net. So that way we allow our network to optimally scale and shift this normalized ranges of our data. Okay. So questions about this metronome intuition? And even if yeah, although we haven't posted our next homework, but yeah, in the assignment, I mean original assignment 2 in the CS231N, yeah, we only yeah, sent out our homework asking you to solve the fifth one, the last one, right? If you have checked the homework, and it asks you to solve only the last one among the entire assignment 2, right? So in that case, the fifth one is the most easiest one, and actually the first 4 is actually asking you to build up or draw the computational graph of this batch normalization, for example. And so in this case, you should be able to draw the computational graph of this batch normalization, and that way you can derive the backpropagation corresponding to what is our parameter in our batch normalization. The parameter will be beta, gamma, and beta, right? So these two are the trainable parameter, right? So we have to anyways compute the gradient with respect to gamma and beta, right? So in order to do so, you have to build up the computational graph for this batch norm. And also, this batch norm will provide the from the entire as a part of the computational graph in our entire network. It will give you the gradient with respect to gamma and beta, but also it will slightly change the gradient with respect to the input value of this x, right? So yeah, so in this case, previously this output node from the linear combination will just be passed through the ReLU unit, right? And then we can compute the gradient with respect to that node x, which is our input to the ReLU. But we now have the additional layer between this linear layer and the ReLU, which is our batch normalization, right? So that batch normalization will add some part in the middle of our computational graph, and thus the gradient arriving at this node will be different, right? So yeah, so that way you basically have to compute df over d gamma or d beta, and also of course you have to compute the df over dx, right? So that dx as an input to the batch normalization will certainly be different from dx or gradient corresponding to this node. So yeah, you have to be able to derive those kind of computational graph and corresponding gradient values for this batch normalization layer. Any questions? And now, let me discuss why this batch normalization has the effect of the regularization. So, why does it have the effect of the regularization? So, what's the meaning of the regularization? So, the main idea of this regularization is, intuitively, regularization main idea is that we don't want to rely entirely on our training data, because it might lead to the overfitting, right? So what would be kind of alternative approach of this batch normalization? So why should so let me ask in this manner. So rather than using just a small mini batch, so if our mini batch size is 20 but our training data is 100, right? And then we can use the mean, the first step of the normalization that makes the distribution of our output of a particular node as a zero mean and the univariance, and then we can do this kind of normalization on the entire training data, 100 data items. But instead of doing so, why do we only use the batch and then compute the mean and the variance from that mini batch and then use it to normalize that data? So certainly it is estimating the mean value and the variance value from our data, right? And at a particular node, if our training data has 100 data items, and then we can collect 100 samples corresponding to that node. And certainly we can use the mean and the variance of the entire training data to normalize our data, right? But that is relying entirely on our data, right? But in the case of batch normalization, we only use the mini batch to compute its mean and the variance and use it as a normalization kind of a constant for our data. So at each different mini batch, they will have slightly different mean and the variance, right? So for the first mini batch, we are talking about the first step in the batch normalization. So in the first step, we are applying different mean and the variance in the first step of a batch normalization, right? So we are making the we are using different values to normalize our data, right? So those values are not exact value compared to the mean and the variance value for the entire data, right? So it can be viewed as having some noise, right, compared to the more reliable values computed from our entire data. But that actually may help to increase the performance for our test data, right? So anyways, so those mean and the variance, even if they are computed from the entire data, so still those values are not perfect value for the true mean and the variance of our maybe entire data. So I mean, training data is only a subset of the data available in real world, right? So even if we compute the mean and the variance from that entire data, that may be just also like have some noise. So in that case, for each mini batch, we just use a different mean and the variance value so that we can impose some possibility of having an inaccurate estimate of these mean and the variance values. Okay, so that way, kind of this adding little noise or using a different, slightly different mean and the variance values to normalize our data. So that actually helps to maintain the good performance for our test data. So that's the effect of the regularization. Okay, so the time's up. So so let's meet again next week at next Tuesday. And also, in terms of an overall timeline, so for the project, I postponed. I mean, I'll ask you to submit the project proposal after the midterm exam. So before then, you can just focus on the preparing for the midterm exam, and then once we learned about recurrent neural network and the attention models, and then that's the time you think of this project topics. So I'll give a project kind of schedules, send an announcement about it. Okay.
배치에서요. 만약에 50개 트레이닝 데이터가 있으면 10개로 나눈다고 하면 미니 배치. 이게 다 베타박 한 마를 공유하는 건가요? 내가 업데이트하고 얘도 업데이트.
네, 그것도 좋은 지적이고, 베타감마는 공유해요. 그러니까 이제 베타감마는 우리 네트워크의 이제 파라미터잖아요. 네. 그래서 그러니까 파라미터는 항상 공통이고, 첫 번째 배치, 두 번째 배치를 적용할 때 그때 뭐 이렇게 공통의 파라미터들이 적용이 되는 거잖아요. 네. 그러니까 베타감마도 역시 공통적으로 적용이 돼요.
네, 처음 그러면 초기화는 그냥
초기화요. 초기화는 이제 감마가 스케일링이니까 감마는 1, 베타는 0으로 하는 게 가장 이상적이겠죠.
처음에 그렇게 한 다음에.
네. 그러면 이제 그 배치 노멀라이제이션의 그 두 개의 단계에서 첫 번째 단계만 역할을 하는 거예요. 두 번째 단계는 그냥 자기 자신으로 그냥 하는 거고. 네, 그래서 일단은 이 레인지 자체를 일단 난리니어 유닛 기준으로 했을 때는 딱 그 가운데로 딱 맞춰주기 때문에 일단은 그레이디언트 측면에서 잘 흐르게 돼요, 뒤쪽으로. 네, 그래서 이제 이게 학습을 굉장히 좀 용이하게 혹은 학습을 좀 빠르게 해주는 그게 좀 있고요. 뭐 데드렐르든 다 파지티브든 이런 뭐 하여튼 그레디언트나 이런 게 다 좀 죽고 이래서 이 랜덤 이니셜라이제이션에서부터 시작을 하게 되면 이제 로어 레이어 쪽까지 그레디언트가 잘 살아서 못 오거든요. 근데 이제 그거는 최소한 다 방지를 해줘요. 근데 그 레인지 자체가 우리의 퍼포먼스를 위해서 가장 이상적인 레인지냐 이거는 또 다른 문제이기 때문에
학습을 통해서
그렇죠. 이거를 감마 베타를 통해서 학습을 통해 이거를 알아서 네가 찾아라라고.
감사합니다.
그럼 그 렐로 설명하실 때 엣지가 중요하다고 하신 게 그거 안 쓰인다고 하신 거잖아요.
네.
그러면 웹사우트에서 만약에 똑같이 한쪽에서 우세하다면 그 나머지 레이어 똑같이 그냥 죽는 걸로 생각하지.
그렇죠. 네.
그거 중간 과정에 10% 20% 죽는 게 그러니까 그러면 더 이상 업데이트가 안 된다는 소리잖아요.
네.
앞으로 남은 스트링의 정보에 대해서 업데이트가 안 되면 이제 뭔가 되게 우연이어야 될 것 같은데 우연이어야 남은 데이터가 전부 대해서 마이너스가 될 것 같은데
네.
그게 20%면 전체 5분의 1인데
네.
그게 그렇게 되는
그러니까 그게 되게 힘든 일인데 그게 어떻게 그렇게 되냐?
네.
그거에 대한 어떤 구체적인 그 과정 자체는 잘 모르겠는데 일단 저기서 얘기한 거는 어떤 네트워크이든 우리가 크게 일단 잡아놓고 그 다음엔 그거를 이제 우리 데이터로 트레이닝을 하는 거죠. 그러면 그 중에 이제 한 20%, 뭐 10%, 20% 정도가 그러니까 트레이닝이 다 끝나고 난 다음에는 그 노드가 데드렐로 혹은 그 다시 말하면 그 리니어 컨비네이션 아웃풋이 항상 마이너스 값으로 나온다라는 거잖아요.
네.
네, 그런 식으로 저기 네. 그러니까 트레이닝이 다 끝나고 나서 우리
아.
네트워크를 이렇게 하나하나 분석을 해봤을 때 각 노드마다 발견되는 그 트레이닝 데이터를 다 넣었을 때 그 값들의 스태티스틱이
네.
이제 다 마이너스로 해갖고 실제로 데드렐로인 애들이 꽤 많이 있다는 거죠.
아, 네. 맞아요. 갑자기 원래 알아는 헷갈린 게 두 개여도 그 제로인인 거 아닐까요?
네? 아, 미는 제로예요.
네. 그러니까 그 절반
아,
해서
네, 네, 그래요. 미는, 네, 민을 고쳐주고자 하는 건 아니고,
네네.
그렇죠. 그 이니셜라이제이션은 베리언스가 좀 초점이에요. 그거를 좀 제대로 설명을 못했는데, 이제 아까 여기서 나오는 게 그 베리언스가 이렇게 뭔가 이 모든 레이어에서 이제 파라미터들을 같은 베리언스를 가지는 이제 노멀 디스트리뷰션에서 뽑으면 그게 이제 그 각 레이어에서의 값들이나 이런 게 노드 수나 이런 거를 다 고려하지 않았기 때문에. 파라미터들이 다 대충 얼추 같은 값들을 가지고 있다면 언제는 이게 처음에 우리가 인풋을 잘 이렇게 만들어줘서 네, 이렇게
죄송한데 저희가 7시부터 시험이 있거든요.
네.
그래서 저희가 대관을 6시부터 9시까지, 8시까지로 잡았는데
네.
수업이 늦어지시는 거예요?
한 10분 정도 괜찮으신가요?
저희가 6시 45분까지 입실이어서
그래요? 그러면 지금 네. 알겠습니다.
죄송합니다.
네. 일단 나가서 얘기를 해도 되니까 일단 뭐 챙기면서 얘기를 하면 어쨌든 그거를 네. 그러니까 그거 같은 걸 쓰면 저렇게 이제 액티베이션이 다 0으로 가까워지거나 아니면 이제 액티베이션이 계속 그러면 그거를 그러니까 그 각 레이어마다 우리가 갖고 있는 그 인풋 아웃풋 노드 개수들도 다 다를 수 있고 막 이렇기 때문에 그렇기 때문에 각 레이어마다 그거에 맞추어서 그 파라미터 값들의 이제 그 매그니튜드를 그거에 맞춰서 어댑티브하게 결정을 해줘야 된다라는 게 이쪽에 그거예요. 네. 그러니까 제로미는 그거는 그거를 바꾸고자 하는 게 아니라 베리언스를 좀 항상 같은 일정한 값으로 컨트롤하자라는 게 이 해나 이쪽의 취지예요. 네.
Once the midterm is out.
Yeah, right. So I send an announcement